physicists were charged with excitement as they witnessed the highly anticipated launch of the most advanced high-energy particle collider. After years of relentless waiting, they finally observed this monumental advancement poised to transform our understanding of the universe. The Large Hadron Collider (LHC), developed by the European Organization for Nuclear Research (CERN), became operational in September 2008 following an extensive construction phase. However, it took a significant amount of time to bring the machine to fruition. Since then, the LHC has played a crucial role in unraveling many of the universe's great mysteries during its various experimental runs. Recently, however, developments have raised concerns among scientists at CERN. After ramping up the collider to a new peak energy level, they identified something unexpected and alarming. Subsequent investigations have led to various theories attempting to explain this anomaly, but these remain speculative. The universe is filled with unexplained mysteries, and over the years, researchers have dedicated their efforts to exploring and understanding some of them. These mysteries include the enormous black holes observed in space, which are said to possess such strong gravitational pull that not even light can escape, as well as the enigma of the Bermuda Triangle, known for the mysterious disappearances of over 50 ships and 20 planes. However, many of these mysteries remain unresolved due to the limitations of technology. In the mid-20th century, physicists sought improved methods to examine the fundamental building blocks of matter. In 1932, physicists John Cockcroft and Ernest Walton created the first functional particle accelerator. These accelerators are essential for studying the fundamental components of matter by accelerating particles to high energies and colliding them. Through these collisions, scientists can observe interactions and test the fundamental forces and particles that make up the universe. Given the importance of particle accelerators in uncovering infinite secrets, CERN constructed the world's largest particle accelerator. Recently, however, researchers have suggested that this particle smasher could potentially trigger the Mandela effect due to its ability to alter the fabric of reality. The Mandela effect refers to the phenomenon where groups of people remember events differently from how they actually occurred. This term was coined in 2009 by Fiona Broome, who discovered that she and many others mistakenly believed Nelson Mandela had died in the 1980s, despite his actual death occurring in 2013. Various factors, such as false memories and the powerful influence of social media and the Internet, can contribute to this effect. Nevertheless, some researchers have raised concerns that previous upgrades to the LHC could have already induced the Mandela effect, dismissing these worries as mere paranoia. Notably, prominent scientists and other public figures have expressed their concerns about the implications of the Large Hadron Collider. Stephen Hawking was among the first to voice his fears about the collider's potential to create black holes that could threaten the universe. Similarly, Dr. Carlo Rovelli shared his concerns in a blog post, suggesting that the LHC might produce exotic theoretical particles that could alter surrounding matter. Renowned astrophysicist Carl Sagan and science fiction author Arthur C. Clarke also raised alarms about the collider, suggesting that it could create bizarrelets or even a black hole capable of swallowing the Earth. During a press conference, President Obama also expressed worries that the collider could trigger a catastrophic event affecting reality itself. The diverse concerns raised by scientists, researchers, and celebrities underscore the gravity of these apprehensions. While the outcomes cannot be predicted with certainty, it is crucial to carefully consider the potential risks and make informed decisions about operating the collider. The LHC, currently the largest and most powerful particle smasher in the world, was built between 1998 and 2008 with a collaboration of over 10,000 researchers from more than 100 countries. It became operational on September 10, 2008, and is the latest addition to CERN's accelerator complex. The collider aims to test various particle physics theories, including studying the properties of the Higgs boson, searching for a wide range of new particles predicted by supersymmetry, and exploring other unresolved questions in particle physics. The LHC consists of a 27-kilometer ring enclosed by strong magnets that accelerate particles to high speeds and energies. Inside the collider, two beams of particles are accelerated nearly to the speed of light before being directed to collide. These beams travel in opposite directions through separate tubes known as beam pipes, maintained at an extremely low pressure. The beams then follow a circular path around the collider due to the intense magnetic field generated by the magnets. Lead particles are the preferred choice for this program, and they are accelerated to an energy of 2.3 trillion electron volts, TeV, per nucleon or 522 TeV within the LHC ring. The LHC operates with an immense amount of energy and produces vast data, highlighting the scale and significance of this scientific endeavor. During LHC operations, the CERN site consumes about 200 megawatts of electrical power from the French grid, roughly equivalent to 1/8 of Geneva's energy consumption. Notably, the LHC and its detectors contribute approximately 12 to 20 megawatts to this demand, exceeding the energy used by previous relativistic heavy-ion colliders. The heavy-ion program aims to investigate quark-gluon plasma, a state of matter believed to have existed shortly after the Big Bang, providing insights into the fundamental nature of matter and the universe. With the help of this particle smasher, one of the major hypotheses in particle physics regarding the existence of the Higgs boson has been confirmed. The Higgs boson, often referred to as the God particle, was detected at CERN in 2012, marking a significant breakthrough in the field of particle physics. If you're wondering about the origin of the Higgs boson's nickname, it comes from a book titled The God Particle by Leon Lederman, published in 1993. However, this nickname has faced criticism from many physicists for potentially misleading the public regarding what the particle actually represents. The Higgs boson is a subatomic particle in the standard model of particle physics, emerging from the excitation of the Higgs field. In the standard model, the Higgs particle is a massive scalar particle with zero spin, no electric charge, and negative parity, associated with mass. Furthermore, the particle is highly unstable, decaying into various particles almost immediately upon its creation. The Higgs field, which resembles a Mexican hat shape, is an invisible energy field that permeates the universe
field,
and is
which is
essential for
electrically
giving
charged
particles
and
their
neutral.
mass, plays a crucial role in how particles acquire mass. This process is explained by the Higgs mechanism, and the associated particle, the Higgs boson, is named after Peter Higgs. In 1964, he, along with 5 other scientists, proposed the existence of this particle. After extensive research, scientists finally identified a particle with the expected properties of the Higgs boson at the Large Hadron Collider, LHC. Discovering the Higgs boson was significant because it explains why some particles have mass, a fundamental characteristic that influences their interactions and behavior, forming the building blocks of matter. Higgs bosons are produced during high-energy particle collisions at incredible speeds. Occasionally, a Higgs boson emerges from such a collision, but it decays quickly, making direct observation challenging. Instead, scientists analyze the decay products and check if their patterns match predictions for the Higgs boson. If the decay patterns are consistent, it suggests that a Higgs boson was indeed created. However, generating a Higgs boson in collisions is rare, and various other collision types can yield similar results. Therefore, researchers must sift through trillions of collisions to ensure they can identify the same decay patterns across different detectors and confirm they are not just random background events. Extensive scientific studies have been conducted to explore possible connections between the Higgs field and cosmic inflation, a theoretical field proposed to explain the rapid expansion of space during the universe's earliest moments. Some theories suggest that a significant field like the Higgs field might be responsible for this phenomenon. The future and nature of our universe have become areas of intense scrutiny because, according to the Standard Model, the vacuum state of the universe could remain stable for a long time, yet it is not particularly stable. This instability means that the universe could become more stable in the future, potentially altering everything we currently understand about it. The stability of the vacuum that contains the universe depends on the properties of the Higgs boson and the top quark. If the universe resides in an unstable vacuum, it could lead to dramatic changes in the distant future. To predict what may eventually happen to the universe if the vacuum stability changes, precise measurements of the top quark mass are essential, which can be accomplished using a specific type of collider known as an electron-positron collider. Scientists also believe that the Higgs field acts as an energy source filling the vacuum, influencing the extreme energies observed in the universe's early moments. This concept implies that the Higgs field has undergone several changes over time, shaping the forces seen in the universe today. Currently, researchers are investigating the relationship between the Higgs field and the energy present in empty space. The energy observed in today's vacuum is minimal, yet theories involving the Higgs field suggest it should be much higher, presenting a significant challenge in physics known as the cosmological constant problem. Looking back at history, we can see how particle physics has evolved, enhancing our understanding of the fundamental building blocks of matter and the forces at play. In the 1960s, scientists faced challenges trying to unify the electromagnetic and weak nuclear forces using quantum field models. Theories from that time, such as the Y-factories hypothesis, predicted that certain particles we thought had mass were actually massless, creating significant issues. Additionally, the Goldstone boson hypothesis introduced the concept of massless particles known as Goldstone bosons, complicating matters further. Initially, researchers did not focus on this hypothesis, but it eventually gained attention, thanks to significant contributions from scientists like Martin Veltman and Gerard T. Hooft. Their advancements helped resolve several issues in particle physics and contributed to the development of the Standard Model. Integrating various forces and particles into a unified theory required overcoming numerous theoretical and experimental challenges. The discovery of the Higgs boson was a pivotal moment in this journey, confirming the existence of a fundamental particle that provides mass to other particles and solidifying our understanding of the universe at the smallest scales. However, the Standard Model is not the ultimate theory of everything. While it effectively describes electromagnetic, weak, and strong nuclear forces, it does not incorporate gravity or explain some of the universe's most significant mysteries, such as dark matter and dark energy. The discovery of the Higgs boson has been a crucial step, but it also highlights gaps and unanswered questions. For instance, although the Higgs mechanism explains how particles acquire mass, it does not fully account for the discrepancies observed in the cosmological constant, which measures the vacuum energy of space. Furthermore, the search for a unified theory that incorporates all fundamental forces, including gravity, continues. Theoretical frameworks like supersymmetry and string theory propose potential pathways beyond the Standard Model, yet they remain speculative and require further experimental validation. The Large Hadron Collider plays a vital role in exploring these possibilities, as its high-energy collisions allow for deeper investigation into the fundamental structure of matter and the forces governing it. While the LHC and the discovery of the Higgs boson represent significant milestones in particle physics, they also open new avenues for exploration, prompting ongoing research at CERN and other particle physics laboratories worldwide. The goal is to address the remaining questions and enhance our understanding of the universe's fundamental nature. As scientific knowledge advances, we can anticipate new discoveries that may reshape our comprehension of the universe and the underlying principles that govern its behavior.